Which of the following is the ionic compound, do you think? D? Does that sound about right? Oh. Oh. An attraction between a positive and negative ion is an ionic bond? Yes? Yes. What did you probably kind of say that that would have been in science 10? Yeah, you probably said a bond between a metal and a non-metal. Right? And then through the bonding unit, you're kind of like, oh, it's about an electrostatic attraction, which was a new word, two oppositely charged ions, which is just a fancy way of saying positive and negative attract. Right? And then the dot and cross diagram are different because we're not sharing a pair, but rather it is negative and it is positive. And that was something that tripped up a lot of you on your midterm. Right? On the midterm, you mixed up that one was ionic and one was covalent. So one is shared and one has little square boxes around. Hands up if you mix those up. Yeah, I've got 4 or 5 hands in the air. I bet you there's only about 2 of you that didn't mix it up in this class. Covalent bond. What did you put for covalent bond, Tristan?
H.
H. An attraction when electrons are shared. Does that sound about right? Good. Electronegativity. There's supposed to be a line there. What did you say, David? Oh, Taylor. That was Taylor. J. J. A measure of attraction for electrons. Yes? What's the word that we used instead of attraction? Affinity. But that means attraction, right? So part of like the difference between junior high and senior high, junior high you memorize. Memorize the definition's on the test, the definition's on the worksheet, everything's the same. Senior high, I should be able to phrase things differently, you should still recognize it. Because I'm not actually asking you to memorize a definition, I'm asking you to understand a definition, understand a concept. So electronegativity, the affinity of an atom for electrons, or the measure of attraction for electrons, same thing. Okay? There are a few things, I expect some keywords to be in there, but other than that, yeah. Polar covalent bond. Which one did you put for polar covalent bond? Emilio.
I put C.
You put C, an unequal sharing of electrons. Would that be polar, unequal? Yeah. And sharing electrons, is that covalent? Yep, so that works. Everybody okay? Non-polar covalent would be a perfect sharing of electrons. Remember this, we're talking about this shared pair on that stick. There's a dot and a cross, and we're talking about if this was a weigh scale, old-fashioned measuring thing like they use in the doctor's office still, if I slide that bar over, it then tips the molecule, making it polar. Remember that? So if it's unevenly shared and that pair is closer to one of the things, it's polar. If it's perfectly shared, it's perfectly symmetrical and therefore non-polar. Remember that? Gabby, are you with me? Yeah? Yeah? Okay. So non-polar covalent bond must say equal sharing. Oh, look, G. Metallic bond? Stephanie? I, an attraction between positive ions and the delocalized electrons. Yes. I like the word delocalized in there, but they don't have it in there. Dipole-dipole attraction. Dipole-dipole attraction. F, attraction between polar molecules. London dispersion, Gavin?
I put D.
D, attraction between positive and negative ions. Okay, they're not ions in London dispersion, so it can't be that one. Liam?
B.
Pardon?
B.
B. That's true. It's the only attraction between molecules that aren't polar, right? Every molecule has London dispersion forces. If they're polar, they have London dispersion forces and dipole-dipole. If they're polar with an OH bond or an NH bond or an FH bond, they have London dispersion forces, dipole-dipole forces, and hydrogen bonds. Okay. Bonding electron. What's a bonding electron? Pardon? A is a bonding electron, single unpaired valence electron. Single unpaired valence electron. So, for example, chlorine, the atom, not the ion, looks like that. Right? Where is my bonding electron? Treat it like a clock, 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Where is my bonding electron? At 2-ish, yeah. There's the bonding electron. It is an unpaired, let me read it, a single unpaired valence electron. Okay? And that leaves what to be my lone pair? E, a pair of valence electrons. So where's my lone pair? On chlorine? Any of the other ones. This is a lone pair, this is a lone pair, and this is a lone pair. Okay, do you remember when we were doing our solutions and we had a list of definitions and I said, could you draw a picture for those? And it wasn't about making a right picture, it was about putting kind of all those words into a picture that can then pop into your head so that when you hear electrolyte, in your head you've got this picture of a light bulb into some solution and then hopefully you've labeled that solution. So you're thinking, oh yeah, acid was there in NaCl. So then you think, oh, ionic compounds are electrolytes and acids are electrolytes. Do you remember us doing those definitions and those pictures? It would be a really good idea to do that for this. These are all bonding units, right? These are definitions. Could you identify lone pair, bonding pair, like I have? Could you draw a picture for ionic bond? Could you draw a picture or an example for London dispersion forces? And then if you can, you really understand the concept. If you can't, you don't understand the concept. You're still stuck in that, if I memorize this, I'll be fine stage. Do you see the difference? You guys did really well on that, by the way. Much better than my Chem 30s did. Same sheet. So well done. Really, well done. Okay, so the next page then sort of puts all these things together. So organic chemistry is about molecules, which are covalently bonded. They are mostly non-polar because they're all hydrogen and carbon. And they will then have London dispersion forces only, not dipole-dipole, not hydrogen bonds. Okay? And so all these things sort of apply to this next concept, which is why I think it's such a great little review. Oh, wait a minute, number 2. Explain why atoms bond together. Why do atoms bond together? Come on, what's the key word I've been using loads this year? Make them more stable. Good. Very good, Gabby. Oh, anyway, you write it down. To make them more stable. And how do they make themselves more stable? By getting a full valence shell. And there are 2 ways they can get a full valence shell. One might be, right, so transferring, either adding or giving away that transfer. And that would create what kind of bond? Ionic. And the other way that they achieve a full valence? To share. And that creates a covalent bond. But the object is stability, full valence. Am I right yet? No. So stability, full valence, ionic being the transfer to achieve full valence, and covalent being the sharing to achieve full valence. And that sheet is like your bonding unit. Okay, there's Vesper diagrams and but you know what? Like that's the majority of it, isn't it? The bonding electrons, the shared pair. That's it. That's it. That's the essence. Okay, so in your next, can you turn to this sheet for me? Let's see if I can just rotate this see if I know how to do this. View, rotate. Look at that. This way, please. Okay. Okay, so crude oil, the one that we've been talking about all along, when they suck that into the ground, or when they take bitumen out of the tar sands, it's a mixture of hydrocarbons. You've heard me say that a lot, right? Mixture being just a bunch of different things all mixed together. Mixture. But actually, I could take one and I could separate them out, or I could take a group and separate them out. Everybody okay with that? Okay. So these exist in carbon chains. And we talked about how bitumen's a very long carbon chain and how I could chop it up or crack it into the shorter carbon chain. Do you remember what we use for airplanes? What's the fuel source? Kerosene. Well done. What do we use for cars?
Diesel or octane?
Octane. And diesel. And octane is how many carbons do you think? 8. And diesel is, do you remember? I said it to one group. I don't know if it was your group. 14. 14 carbons is diesel. So these all have names, like octane for 8 carbons. So this little sheet here is going to help us understand their name, how many carbons long, how many hydrogens does that mean, and why does it look the way it is. And then at the same time, it's going to also remind us about bonding electrons and dot and cross diagrams and Vesper diagrams, and it's a nice little review for us. So does anybody know if we have the molecular formula, by the way? Oh yeah, at the same time, you're kind of learning the definition of a molecular formula. The definition of a Lewis, not necessarily the definition, the application of a dot and cross diagram or a Lewis diagram, which is review, right? The definition of a display diagram, the definition of a structural diagram, and the review of a Vesper diagram. So at the same time, we're kind of not only just learning the names and how they look, but also the category and what that title means on the category. Okay, so you kind of are learning 2 things at the same time. So molecular formula being all of the carbons and hydrogens sort of grouped together. So C1, which we never draw the 1, do we? We never put a 1 down in our chemical formulas. H4. Do you know what that's called? Do you remember anybody? It's kind of one of the normal ones that might be on a list of compounds you should know the normal names of, like glucose. Methane. Methane. So this is called methane. Without looking on the other sheet. The other sheet's there so that it's nice and neat for your notes. But this is the learning of it. Dot and cross diagram. Can you draw the dot and cross diagram? Do you remember how to draw dot and cross diagrams? Do you remember where we start? What do we start with? Liam's already on his way. So what did you start with, Liam?
I put the C down.
You put the C down. Why do you put the C down in the middle? We always put the C down in the middle. Why?
The most bonding.
The most bonding electrons. How many bonding electrons does C have? 4. Well remembered, because it's in group 4 if you had to look it up on the periodic table. And conveniently, it has 4 bonding electrons, and I need 4 hydrogens. And so one sits here, and another one sits there, and another one sits there, and another one sits there. This is why it's C4 and not C3 or C5. There isn't a spot for a 5th one. This is why it's CH4. The display diagram is converting those dot and crosses into sticks. Okay, so the dot and cross becomes a stick, that dot and cross becomes a stick, and another stick, and another stick. Are you okay with that? For now, with these small ones, there's no difference between structural diagram and display diagram. So my structural diagram is going to look exactly the same. What Vesper diagram does this have? Do you remember out there? Tetrahedral. Do you remember how to draw a tetrahedral? So I'm going to write tetrahedral. Do you remember how to draw a tetrahedral? Yeah. How do you do it? See how many sticks?
4.
Oh, on a Vesper diagram? There's 2 sticks. And what else? A triangle, which is called a wedge. Although it sometimes is called a delta, but not here. So a wedge and those dashes. And do you remember what it looks like? Well, we'll get it out of the cabinet and show you. Do you remember? A tripod with a camera on top. Right? Ignore that one, please. Ignore that one. But here, look at this one. So this one's got a chlorine on one of the sticks, but anyway. So there you go. Okay, so a stick up, a stick along the plane of the paper. Oh, I'll turn it this way so it's the same as on the board. This one's going towards you and this one's going away from you. Tripod with the camera on top. Remember that? Okay, so the next molecular formula would be C2H, in fact I'll change colors so we can see it a little bit more, 6. This one's called ethane. Dot and cross diagram. Can you do it? Can you do it on your own? Okay, have a go. Okay, does your dot and cross diagram look like mine? Does your display diagram look like mine? All right, so now this is the difference between a display diagram and a structural diagram, okay? Displayed means like a display cabinet. Everything is out for you to see, okay? Nothing's hiding, everything's like a peacock displays its feathers. Everything is sticking out. Structural diagrams kind of can be grouped together a little bit. There's a whole variety of structural diagrams you can have. Lots of different ways you can do structural diagrams. It just means it's not all smucked together like this. That's all smucked together. The molecular formula, all the carbons are together, all the hydrogens are together. And if you had something like C100, H202, you wouldn't really know if they were all in a long chain, if there were branches, if it looked like a T, if it looked like an X, or if it looked like a big straight line. You wouldn't know how to put those 100 carbons. Does that make sense? A structural diagram shows you a little bit about whether it's a T, an X, or a line. Okay, so, and they're a little bit faster to write than a displayed diagram. So the structural diagram, I'm going to write CH3, CH3 for this one. Can you see where I got my CH3, CH3 from? And do you see it's a little faster? Okay? It's a little faster, but there's more room for error. This, it's very easy for me to see 4 sticks. Remember, 4 things on carbon, 4 sticks. 4 sticks, no problem. Here, it's a little bit trickier to see the 4 sticks. You gotta kind of make sure you know what you're doing. So it's faster, but more room for error. Okay, structural diagram, the Vesper diagram, I mean. What's gonna be the shape around this central carbon? Tetrahedral. And around that carbon? Tetrahedral. 2 tetrahedrals. So both of them tetrahedral. And do you remember how we draw something that's like a little bit more complicated? How do you do that, Steph?
So off the second stick, let's say.
Off the second stick?
Yeah. Then that would attach to the other carbon.
Right. So we always keep going on a stick so that it's easier for us. If you go on a wedge, you're a little bit not sure if it's sticking out or what, right? So stick like this. Oh. Can you see that? That's a little bit messy. Okay, so that's where we start. Yes?
I feel a little bit nauseous. Can we go?
Of course you can. And then this is going to be a stick and a dash and a wedge as well. Okay, so 2 tetrahedrals. Sam, can you just go with him? Make sure he gets to the toilet, okay?
Yeah.
Thank you. So, can you see why carbon and hydrogen molecules are never polar? Is tetrahedral is nonpolar, right? The other tetrahedral is nonpolar. So if this is nonpolar, everybody okay with that? That's nonpolar. Do you remember that from the unit? So putting two nonpolar things together, guess what? Nonpolar. What's going to happen when I attach another C and its hydrogens on the end? That'll be tetrahedral as well. And so then I'll just have three nonpolars all in a row. Okay, so all of these will be tetrahedral around each carbon, and therefore non-polar. And then we don't have to draw the tetrahedrals anymore as long as we understand that. Okay, as long as we understand they're all tetrahedral around each carbon, non-polar. Okay? Everybody all right? Switch colors. C3H8 is called propane, as in like a propane tank. And I'm sure you could draw the dot and cross diagram and display diagram for that and structure diagram. Could you also, at the same time, do for C4H10, which is butane, which is in your butane lighters, your Bic lighters, Zippo lighters. They have butane in them. And C5H12, which is pentane. Okay, so do your dot and cross diagram, your display diagram, and try your structural diagrams for those three. I'll pause the video, and then we can do those ones. Okay, and then we'll keep going. I'm going to do 10 in total, just so you know how long you can make your sheet. Are you running out of space already? Okay, don't worry, we'll sort it out. Okay, C, good. Where did we leave off? Because the board always wipes out as soon as I touch it. No, C, which last one I did for you? C2. So C3, last you do on your own, I should say. C3H6, C4H10, C5H12. Okay, so this name was propane, this name is butane, and this one is pentane. Dot and cross diagram for prop would be kiss and a hug, H, kiss and a hug, H, kiss and a hug, H, kiss and a hug, C, kiss and a hug, H, kiss and a hug, H, kiss and a hug, C, kiss and a hug, H, kiss and a hug, H, kiss and a hug, H. All good? Display diagram then converts each of those kisses and hugs into a stick. Everybody give me that? And the structural diagram then kind of condenses it a little bit, but not as condensed as the molecular formula. And so you could have CH3, CH2, CH3. And Taylor asked, do I need a stick there? And I said, it doesn't matter. You can put a stick there, you could not put a stick there, whatever you fancy. Still be structural. The Vesper shape would be tetrahedral, and how many tetrahedrals? 3 of them, and I said you don't need to write them anymore, we can just know that they're going to be all tetrahedral around each carbon. Right? So over here, butane, do I have to draw the kisses and hugs, or do you think you're all right? You think you're good? Yeah. Okay, so the display diagram would be 4 carbons in a row, and then hydrogen, 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 hydrogen. Yes? And then the structural diagram would be CH3, CH2, CH2, CH3. Hands up if you're like, yeah, I totally get it. Good. Fabulous. So pentane then would be CH3, CH2, CH2, CH, I've lost count, 1, 2, 3, 4, 5. And the structural diagram would, or display diagram would look like this. 1, 2, 3, 4, 5. All H's. Note, I've got 4 sticks on my carbon. Yes? When we get into the trickier ones, you will make a mistake and you will put 5 sticks on your carbon. Or 3 sticks on your carbon. And I will say to you, there's 3 sure things in life. Death, taxes, and 4 bonds to carbon. Okay? You will die, you will pay tax, and there's always 4 bonds to carbon. Okay. Even in graphene. It's just a less stable bond. Okay, so hydrogen, 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 hydrogen. Happy? Happy. Okay, so this is going to disappear on me. We're now at C6H14. Good one. Good. C7H16. You seeing the pattern yet?
Yeah.
C8H18, C9H20, C10H22. These are called hexane. What do you think C7's called? Hexane. C8. Octane. These are just like these mathematical symbols, right? And what's 9-sided figure in math? Nonane. And a 10-sided figure? Decane. Don't bother doing the dot and cross diagrams now, because I'm trusting that you know how to do them. Can you do the display diagram and the structural diagram? And don't do the Vesper diagrams, because we know that they are tetrahedral around each carbon. Done. Sorted. Dot and cross diagrams are getting a bit nauseous now, so we'll just do the displayed and structural. Okay, so all of my sticks have hydrogens on them. I'm just not writing them down because I'm lazy, but they're all there. And then you would have gone like this: CH3, CH2, CH2, 1, 2, 3, 4, 5, 6, CH3 at the end, 7 times. Everybody with me? I'm going to rewrite this. Watch this. Watch. So remember how I said there was a variety of ways you could draw the structural formula? Yes? This is one way. This is a correct way. This is probably the way you should choose because you're not going to make a mistake. However, one might choose this way. CH3 bracket CH2. I have 1, 2, 3, 4, 5 of those. And then I'm ending with a CH3. See that? Making it still structural, even more condensed than this. Okay. So for my nonane, no, where am I? I think I'm on octane. I'm going to write CH3, CH2 in brackets, and I'll have 6 of those CH2s, and then a CH3 on the outside. And for nonane, CH3 bracket CH2, 7 of those CH3. And for decane, CH3, CH2, 8 of those CH3. 8. This board isn't loving me ever, really. I was going to say today, but this board never loves me. Okay? Happy? Okay, so because yours now looks very messy, but at least you know how to do them. So if I asked you to draw the display diagram for octane, you could. If I asked you to draw the dot and cross diagram for pentane, you could. Okay, so we've practiced all of them. I'd never asked you to do the whole chart, but I would ask you to do one of something. Right? What shape is around the carbons in a decade? Tetrahedral, good. Okay, so I would never ask you to do the whole chart, but you've done it all, so therefore you should be confident in it. And then I gave you another sheet following down or actually I think it's back for you guys, this sheet here, which then, and I will view, rotate it back please. This sheet here then lays it all out for you. Okay, so it's nice and neatly typed up. But now you know how to get there on your own. The other things added to this is that it tells you that it's a gas from number 4 up. Well, pardon me, from number 1 to number 4, I should say. And why do I want you to know that? Not because you memorize it, but because you see these every day. Every day, methane comes into your house and heats it. Unless somebody's house in here is heated by wood burning stove. Anybody's? Okay, so every one of our houses is by natural gas, methane. And you burn it, and it heats it up in your furnace, and that hot air is blown around your house. Or the hot water is then heated, the water is heated, and then the water goes through the floor. Right? So, everybody has seen a Bic lighter. Do you know what I mean? Bic lighter? Everybody's seen one of those? That's butane. Who's seen a propane tank? Oh. And so I expect you to know those are gases because you see them every day. Not because I want you to memorize carbon 1 to 4 gases. No. Because you should know where butane is in life. Okay, and then we end up liquids. Why are these liquids? Why do they go from gas to liquid? Why are those liquids? You know the answer to this from Unit 1. Emilio?
Is it because they're more dense?
Sort of. You're on the right track, but why are they more dense is really what I'm asking. Yes, Stephanie.
They have more intermolecular forces.
Good. Which intermolecular forces? London dispersion. Do they have hydrogen bonds? No, because carbon hydrogen isn't. What is it? It's hydrogen, oxygen, hydrogen, fluorine, and hydrogen, nitrogen, not hydrogen, carbon. And are these polar? No, right? That was the whole tetrahedral conversation. So no dipole, dipole. So 2 of these liquids together, right? More intermolecular forces means they stick together more. And if you remember in grade whatever, 7 or something, you would have drawn these like this, right? Liquids look like this. Do you remember that? Liquids versus gases look like this. What's keeping these closer? What's keeping these closer? The intermolecular forces, specifically London dispersion forces. Why do they have more London dispersion forces than these guys? Why, Tristan?
There's more of them.
There's more of them. What do you mean?
The London dispersion forces are stronger because there's more dispersion forces between.
Okay. Why are there more London dispersion forces? Why are there more London dispersion forces?
So there's a greater number of carbon atoms.
Right. Do you remember what London dispersion forces were? The attractions of the electrons in one attracted to the protons in the other molecule. Remember that whole thing about a stadium and across the stadium? Not a bond, but an attraction. And likewise the other way. Remember that? And if you have a bigger stadium, you'll have more attractions happening. More electrons, more London dispersion forces. So the more carbons, the more electrons I'll have. Remember? Yes. Yeah? So more London dispersion forces because more carbons, which means more electrons. Therefore, stronger intermolecular forces sticking them together, therefore liquid. Yeah, write it down. Okay? Less London dispersion forces equals less energy needed. Well, actually, that's a bad argument because that's more going towards boiling point. So I'll say less energy holding them together, forces. Equals gas. This is all room temperature, right? You must know that. You must know it for Chem 20. You must know it for Chem 30. It is like one of the hardest things that students do are these intermolecular forces. Do not be the student that buries their head in the sand and prays to God that it never appears. It will. It will. In fact, in your midterm, I think there are about 8 questions on it. Right? So you gotta know it. That's a lot, it's a big percent. I can't remember how many it was out of. Let's say it was out of 34 or something. You figure out what 8/34 is. That's like 30% or something. Okay? Know it. It's important. Don't bury your head in the sand. If you don't know it, figure it out. If you can't figure it out, come see me. It's important. Okay, so, and then the names are there. Meth, F, prop, but, pent, hex, hept, oct, non, and dec. Okay? You have to memorize all the way up to 10. Yes, there are more. There's 11 and 12. Dodecane is 12. Centane would be 100. Right? But you don't need to memorize those ones. You just need to memorize up to 10. And you should already know dec, non, oct, hex from math. The first ones, though, they don't follow our lovely little math thing. Right? 1 to 4, that doesn't follow our math. It should be like try for 3, not pro. So, a student once said to me, this is how I'm going to memorize it. And for some reason, it spread like wildfire, and all of my students then loved it, and they also memorized it. And every time I say it to students, they go, I like that, and they all memorize it. It's stupid and it's silly, but that's how students memorize it. So it goes monkeys eat peanut butter. And then pent like a pentagon, hex like a hexagon, duh. Monkeys eat peanut butter. And you'll be amazed how many students write it, get their test, they write monkeys eat peanut butter at the top. Okay? So use it to memorize meth, F, prop, but. So those are the hard ones. Pent, and the rest are like math. And pent and prop often get mixed up by students just simply because they both start with P. And so students tend to, mean pentane and they put propane, or the other way around. Okay? So monkeys eat peanut butter, and then the rest are like the math. Questions, comments, concerns? No, monkeys don't eat propane.
No, I said purple bananas.
Purple pants?
No, purple bananas.
Purple bananas?
Yeah, because they eat bananas, but I didn't know what
Do you think monkeys might eat peanut butter if they had peanut butter?
Yeah.
Okay, so, but here's the thing. That would be done in the organic unit if that was it. Except for these are all lovely long chains. And they don't all look like lovely long chains. They have branches off of them. So we have to have a whole new naming system. So, I'll show you an example. Oop, oh, was at the end of the, oh dear, oh no. Okay, hold on. Let me pause this video, let me find.